guys, nice to see you. How are you doing? So, let us recall our previous discussion, which was the Otsawart law, and what it helped us to uh, determine magnetic field created by some electric current in a conductor or parts of some like beam of positively or negatively charged particles which are moving in free space. So let's say we are considering some length segment of a conductor, ds, and define it as ds vector. What can we tell about magnetic field, which is created by this length element ds vector in some point P next to the conductor, if there is electric current with magnitude I flowing through the conductor. So what can we tell about dB vector, created magnetic field created specifically by this small length element ds vector?
They're perpendicular to each other.
So that's good. So what is perpendicular to what?
dB perpendicular to ds vector.
ds vector
Also,
and
r vector.
r vector, which, well, we could represent it as position vector, which defines the position of point P with respect to this length element ds vector, or it could be just unit r vector, which defines only the orientation. So it's not, there's no difference because dB vector will be perpendicular to both. So what will be the magnitude of dB vector proportional to?
Current.
So first current, like magnitude of electric current which flows through the conductor. Then second,
Inversely proportional to 1 over r squared.
well,
This is
if it's either proportional to 1 over r squared or it's inversely proportional to r squared. So that's also correct. What else?
directly proportional to ds.
To the magnitude of this length element which we have chosen. So the longer this length element, the larger magnetic field. Something decomposing here. So based on these findings, it is possible to create an equation which helps us to calculate both orientation and magnitude of magnetic vector created by this length element ds with current I. So what will define the orientation of dB vector in this equation? So how equation looks? It's like 4 pi mu naught divided by 4 pi times I times the ratio between cross product of ds vector and r unit vector divided by r squared. So in this case, what defines the orientation of dB vector? Cross product of ds vector and r unit vector. And all the rest, including the cross product, also will define the magnitude of this vector. So based on this law, we can calculate this dB vector, where that is only contribution from a single length element, in order to get the resultant magnetic field vector, B vector, next to conductor with arbitrary shape. What we need to do?
take integral over this equation.
over the whole conductor and get the resultant magnetic field vector. So that is how we determine magnetic vectors, field vectors, and that is important to definitely keep in mind how it works, because you need to understand how to determine magnetic field vectors in the vicinity of different conductors or beams of electrons or protons. We did some examples how we can apply this Bayes-Savart law in order to calculate the magnetic field vector next to different conductors. So we considered a straight conductor of limited length, also or of infinite length, and also we considered this kind of segment of a circle initially, conductor shape, and then we considered the whole circle, like circular loop, a closed loop of a conductor with electric current I, and determine magnetic field in the center. So now we proceed further, and first we try to get the force which the interaction force between two straight conductors placed next to each other. And next will be Ampere's law, which is similar in some way to Gauss' law for electricity. So it helps us to determine a magnetic field next to certain type of electric current distributions. So that's what we are planning to work on today. Let us start with two conductors. So, and determine magnetic force between two parallel conductors. So we have conductor 1, conductor 2. We have some current I1, current I2 flowing through these conductors. Then let us determine what force F1 is exerted on first conductor from the second conductor, like because of the obviously magnetic field created by second conductor. So there is some distance A between these two conductors, and we can write that F1 vector is equal to I1, electric current which flows through the first conductor, times L vector. L stands for the length of this conductor. Multiply cross product B2 vector. B2 vector stands for magnetic field vector created in the position of first conductor by conductor number 2. And in this case, we have current flowing to the right, and we will have perpendicular orientation of the magnetic field vector B2 created by second conductor. So it will be kind of a circular orientation. So we discussed earlier that when we determine magnetic field created by a straight conductor, it possesses some radial symmetry. So this will be part of this tangential to this circle with radius a, and A stands for the distance between two conductors. So now let us get the magnitude. So the force actually, it will be the orientation of this force will be towards the second conductor. So it will be some attractive force. The first conductor will be attracted by second one because of magnetic field created by second conductor. So magnitude F2, sorry, not F2, but F1, will be given as I1 times L times B2. So since these guys are perpendicular to each other, we have unity for sinus alpha. Then we go for I1 times L, and what will be the magnetic field? Mu naught times I2, current in the second, 2 pi A. No, because this is, instead of R, we use A. Now, so that will be the magnetic field created by second conductor next to the first conductor. Then we end up with the following. It will be mu naught I1 times I2 divided by 2 pi A and times L. So that is the magnitude of the attractive magnetic force. And now, what will be the F1 vector? So according to the third law of motion, we can write that F2 vector will be equal to minus F1 vector. And in magnitudes, they will be equal to each other. So F2 vector magnitude is equal to F1 vector magnitude. So now what we can also introduce here, we can replace them by this magnitude of attractive force with some Fb. So that will be magnetic force which attracts these conductors in that case when electric currents are flowing in the same direction. So if we flip the direction of magnetic current, then this will be repulsive force. So that also should take into account. And we can determine what will be the magnetic force exerted per unit length of the conductor. So we can move this L from the right side to the left. So it will be Fb divided by L equals to mu naught I1 times I2 divided by 2 pi A. So this equation gives us some normalized magnetic force per unit length of two parallel conductors, which carry currents I1 and I2. So this magnetic force, let's call it specific magnetic force, is normalized per unit length proportional to the magnitudes of the currents which are flowing through the conductors and reversely proportional to the distance. By the way, now it's different, but it used to be an important experiment to determine the echelon of 1 ampere. So 1 ampere magnitude of current with 1 ampere was determined as certain force exerted, like some magnetic force exerted between two parallel conductors per unit length at given distance, like some 1 meter distance between them. So that was the way how you could get the calibrated echelon magnitude of 1 ampere. You know what should be this magnetic force. This magnetic force can be measured. Then current was flowed through two parallel conductors, and that was the way how you can calibrate for this magnitude of 1 ampere electric current. However, now it's a bit more advanced approach. So let us move now to Ampere's law. And as I mentioned, let us probably recall what Gauss' law gives us in electrostatics. Why do we care about that?
Flux,
You remember what is Gauss' law?
flux equal to the charge enclosed by the sphere divided to the free space, permittivity of the space.
Yeah. Or permittivity of free space times the electric constant, or if it's in some medium. But if it's in vacuum, you're correct. But we need to specify that the flux of electric field vector through a closed surface, three-dimensional closed surface. So the equivalent of closed surface is just the surface of three-dimensional body. So will be equal to the magnitude of electric charge enclosed in this surface divided by permittivity of free space. So this statement allows us to determine electric field in certain conditions when we have symmetric cases of electric charge distribution in a very simple way, because we know that electric field vector flux will be equal to enclosed electric charge normalized by some constant, and that gives us a lot of a nice tool to simplify a lot these calculations for electric field vector. So similar we can do with Ampere's law. In the case of determining magnetic field vector, and when we have different distributions of electric current in conductors. So that's why that is quite important in field of magnetism. So let us consider some conductor with electric current I. So it will create some magnetic field around it, and this will be a magnetic field vector, B vector. So let us do now the following. We will choose here, let me change the color, some ds vector along this circular path at some distance from the conductor. So this is the radius of the circle which we consider around the conductor. And now we want to do some manipulations, but before we need to specify that ds vector will be always parallel to db vector. Or maybe we can write here just b vector. So it doesn't matter which point we choose, these two vectors will be always tangential to the circle. So they will remain always parallel to each other. Now let us consider integral over closed circle, like closed loop, are dot product of B vector and ds vector. Since they are parallel to each other and dot product magnitude goes with cosine alpha, cosine 0 will give us unity, and magnetic field, will it change if we move around in circle? The magnitude of magnetic field? No, it will not. It will be the same because of the radial symmetry of the magnetic field created by this linear conductor. So we can factor out the constant magnetic field from the integral. Here we have integral over closed loop, like circular loop, and here is ds. So what will be this integral? When we integrate around circle over ds small length element. So we kind of technically divide this circle in small ds elements and sum them up. So what we will have eventually, that will be the circumference of this circle, and that will be 2 pi times r. So will be b times 2 pi r. And we also know what will be the magnetic field, magnitude of magnetic field at this position of the circle next to the conductor with electric current I. So that will be mu naught times I over 2 pi times r. And here we put this part, 2 pi times r. These guys are cancelled out, and we get mu naught times I. So that is a simple example with a linear conductor, straight conductor. However, this conclusion actually can be generalized for all cases. So we can write that in general, that the integral over closed loop, any closed loop, of a dot product b vector ds vector will be always equal to mu naught times I, and this I will be electric current which flows through the area defined by the closed loop. No matter which closed loop we choose, arbitrary shape, but we have closed loop create some area, and the current which flows through this area of the closed loop will be this current in this equation. So that is Ampere's law, which is in some aspect can be applied in a similar way as Gauss' law in electrostatics. So we need to remember this. That's our Ampere's law equation. And now let us try to apply this Ampere's law in order to determine magnetic field next to different current distributions. So let us consider a conductor with some radius of the cross section r. And what we want to do now we want to determine magnetic field, first of all, at some distance r, like small r, from the center of this conductor. So it will be some larger circle. And also we can determine at some smaller circle closer to the center, which is placed inside the conductor. So we have two actually distances where we want to determine magnetic field. So now let us start with the larger one. We know that integral over closed loop for the product of magnetic field vector and ds vector will be equal to b times integral ds. And in this case, it will be b times 2 pi r, which is the circumference of this large circle outside the conductor. And that was equal, according to Ampere's law, mu naught times I. So now we can determine the magnitude of magnetic, the magnitude of magnetic field. B is equal to mu naught times I divided by 2 pi r. In the case when r is larger, like small r is larger or equal to the radius of the conductor. So that is the equation for magnetic field, magnitude of magnetic field at distance r from the center of the conductor, which we derived on previous lecture using Biot-Savart law, but that was taking much more time and effort. Here, when we apply Gauss law, this Ampere's law, we get this equation in much easier way. What is important next, we can also determine the magnetic field inside the conductor when this condition is not satisfied. So when radius, the distance from the center is smaller than the radius of the conductor. So let us do that. So now we consider small r here for a small circle inside the cross section of the conductor. So now we need to take into account one factor, that we always consider that current within the Ampere's law, which flows through the surface of the closed loop which we define. So now this closed loop which we define possesses radius smaller than the radius of the cross section of the conductor. Means that the current which flows through this surface will be smaller than the total current I flowing through the conductor. So we need to determine what will be, so this is some current I, which we use here for calculating the magnetic field outside of the conductor. And now we need to determine what will be the magnitude of electric current, which actually flows through this internal closed surface of the internal closed loop. So how will be the ratio? Let's say if we consider that this current through the internal closed loop, this area, how it will be defined. Let's say it's I prime. It's the current which flows through this internal closed loop surface. Then the ratio I prime to I, which is the current through all conductor, will be what? How we defined it? We consider uniform distribution of electric current density along the cross section of the conductor. If we take this into account, then what will give us the ratio of the magnitudes I prime and I? So we deal with the total cross-section area. There is some current I floating through the cross-section area. Let's say this is area A. And current I. What will be current density? J will be I divided by A. So current density is uniform all over the cross section of the conductor. So no matter which part of conductor we take, like small area, the current density will be the same. Now we consider some smaller area, let's say A prime. What will be the current which flows through this closer area A1 if we know J, current density? We just need to multiply. So current I prime is equal to J, current density, which we already know, times A prime. Then we cancel area and we get, from current density, we get current in amperes. So now the question is, we have I prime, current which flows through the closed loop located inside the cross section of the conductor, to the total current. So what it should be equal to? Actually, ratio between the internal, like loop area A prime, and total area A. So that is 2, no, it's not 2, it's pi r square divided by pi capital R square. From here, we can define expression for I prime in terms of total current I floating through the conductor. So that will be R square over capital R square times I, which is the magnitude of total current. So now we know what current is floating through the area of the closed loop located inside the cross section of the conductor. And at this point, we can apply Ampere's law. So it will give us integral over closed loop B vector dot product ds vector. This is B times 2 pi r, like small r, and that should be equal to mu naught, but not mu naught times, instead of I, we put I prime. Because we don't care about whole current which flows through the conductor, we care only about that current which flows through the area of the closed loop placed inside the cross section of the conductor. And that is mu naught times this r square over capital R square times I. So now we can express the magnetic field, and we will get the expression for B as mu naught times I divided by 2 pi r square times r in the case when r is smaller than radius of the cross section of the conductor. So we have now two equations. Let's write them down. We have magnetic field B equal, this is our first equation, mu naught times I over 2 pi r if r is larger or equal to radius of the conductor. And second equation for magnetic field, which is determined for medium inside the conductor, will be mu naught times I over 2 pi times r square times r, when r is smaller than radius of the conductor. So now we can show graphically how magnetic field will change with the distance inside, like from the internal, from the center of the cross section of the conductor, within the conductor and outside of the conductor. So here will be magnetic field B. This will be distance from the center of the conductor. This will be the radius of the conductor, so we can even so this is like center, and this is the edge of the conductor. So now let us see, this area on axis x will correspond to the internal part of the conductor. So we need to look at this equation. So here in the parentheses we have a constant because current doesn't change, mu naught pi constants, and radius of the cross section of the conductor is also given. It doesn't change. It doesn't get wider or narrower. So this is a constant, and then the only variable is r. So in this case, we have just linear increase of magnetic field. As we go from the central point of the conductor, magnetic field linearly increases up to the surface of the conductor at distance capital R. And then we look at equation in the left when we go further in distance. So we go outside the conductor, and we see that it's in this case magnetic field is proportional to 1 over r. So it will just decay as we go further from the surface of the conductor. So now we, with the help of Ampere's law, managed to build the profile of magnetic field inside should have linear increase, and outside of the conductor. And everything was done with quite little effort due to the application of Ampere's law. Let us summarize our discussion for today. So, similar to Gauss' law in electrostatics, when we could apply this law in certain cases for specific charge distributions to determine in an easy way electric field created by these charge distributions, we can also apply Gauss' law, which tells us to determine magnetic field, which tells us that the integral of the scalar product magnetic field vector and Ts vector along a closed loop of arbitrary shape will be always equal to the product of mu naught and current I. This current is the current which flows through the area of this closed loop. And once we know it, we can apply this Gauss law, Ampere's law, in order to determine the magnetic field for different current distributions. We apply this to the case of a straight conductor, determine how magnetic field changes when we move away from the conductor, from the surface of the conductor in the surrounding environment. And also, we managed to determine what will be distribution of magnetic field inside the conductor. So inside conductor, we have linear distribution of magnetic field, and then so it increases as we approaching the surface of the conductor, and then it decreases as we go away from the conductor. So next time we will consider another example of Ampere's law application in terms of determining magnetic field, so-called solenoid, which provides us with some special current or distribution. And this special current distribution, which provides solenoid structure, allows us to create quite uniform and strong magnetic fields. So that will be our topic of discussion next time on Friday. Thank you very much for attention and see you next time.